This problem explores how the relative masses of two blocks affect the acceleration of the blocks. Block A of mass ma rests on a horizontal tabletop. There is negligible friction between block A and the tabletop. Block B of mass mb hangs from a light string that runs over a pulley and attaches to block A. The pulley has negligible mass and spins with negligible friction about its axle. The blocks are released from rest. So suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. So the magnitude of the acceleration should be very small or even zero. And this is because if the mass of block A is much greater than the mass of block B, logically you can imagine that block A would not move very much, even if block B is released. And here I drew a small comparison. So the fat dude on the table would not be moved very much or even at all by the mouse hanging on the string. And another way to phrase it is that block A has a greater inertia. So by definition, it has a greater tendency to resist acceleration, so its speed will not increase very much. So now suppose that the mass of block A is much less than the mass of block B, and again, estimate the magnitude of the acceleration of the blocks after release. So the magnitude of the acceleration should be very close to the acceleration of gravity, which is 9.8 meters per second. Because in the problem it said that there is negligible friction between the blocks in the table, block B would basically be in free fall if block A's mass was very small, and the pulley also has negligible mass and friction. And here I drew another comparison. So the mass of the bowling ball is much greater than the mass of this small turtle. So if we're not counting in like air resistance or any friction, then the bowling ball would basically just be falling in free fall if it is released. Now suppose neither block's mass is much greater than the other, but that they are not necessarily equal. The dots below represent block A and block B as indicated by the labels. On each dot, draw and label the forces exerted in the block after release. So on block A, because it is touching the table, both the gravitational force and the force of normal will be exerted on the block, but since the block isn't moving in the y direction, the length of the arrows for the two forces should be equal. Then the string connecting the two blocks will exert a tension force, and for block A the tension force is pointing in the right direction along the string, and block B has the tension force going upwards, because if you remember the picture, the string is holding block B at the top, and then the gravitational force of course would also be exerted on block B. And in general, the gravitational force is always exerted unless the problem specifically says that the system is not on Earth or something like that. And there is no normal force being exerted on block B because it isn't touching a surface. Derive an equation for the acceleration of the blocks after release in terms of mass of A, mass of B, and physical constants as appropriate. If you need to draw anything other than what you have drawn, okay. So basically, if you look at the diagram that we made earlier of the forces being exerted on the two blocks, the tension force being exerted on the blocks is the same. And then we can use Newton's laws. So the net force is equal to the total mass times acceleration, and then the tension force should be equal to the mass of A times acceleration, because the force of gravity and the force normal on block A cancel out. So the net force on block A is the tension force. For block B, the net force would be the gravitational force minus the tension force, which would also equal mass of B times acceleration. And so then we can plug in the tension force. So it would be mass of B times G minus the mass of A times acceleration, which equals the mass of B times acceleration. And then we can simplify that equation to get that acceleration equals mass of B times g divided by mass of B plus mass of A. Okay, consider the scenario from part A2, where the mass of block A is much less than the mass of block B. Does your equation from the acceleration of the blocks from part C agree with your reasoning in part A2? And yes, the equation does match up with my reasoning, because if you plug in 0 as the mass of block A, the mass of block B can then be canceled out from like the top and bottom of the fraction. So what is left is simply the gravitational constant. So then the acceleration would equal the acceleration due to gravity. And that does match up with what we said earlier. While the blocks are accelerating, the tension in the vertical portion of the string is T1. Next, the pulley of negligible mass is replaced with a second pulley whose mass is not negligible. When the blocks are accelerating in this scenario, the tension in the vertical portion of the string is T2. How do the two tensions compare to each other? So T2 would be greater than T1, because since the pulley now has a mass that's not negligible, the acceleration of the two blocks would be smaller than the acceleration before. And you can think about it in this way, where the second pulley has more rotational inertia than the first pulley, so that would cause the smaller acceleration. And looking at the formula of force equals mass times acceleration, acceleration is directly related to the net force, so a smaller acceleration would also cause a smaller net force. And then the forces on block B is the force of gravity and the tension force. So the force of gravity is larger than the tension force, because otherwise the block would not move down. So in order for the net force to decrease, the tension force would have to increase, so that the magnitude of the tension force is closer to the magnitude of the gravitational force, and so the difference in their values would be smaller. So that is why the tension force with the pulley that's mass is negligible should be greater than the first tension force.